Hello, everybody. I hope you're all doing well. So, we're going to look at an introduction to rigid body kinetics, and we're also going to look at a very short problem where we derive equations of motion for a rigid body. Okay, so in this particular chapter, we will look at rigid body kinetics. So, rigid body kinetics. And here we are essentially trying to study the relationship between the forces and the motion of the rigid body. Okay, so we study the relation between the forces and the motion of the rigid body. All right, and it is imperative that we know what the kinematics of the body is to do the kinetics of the body. Okay, so something that what I will do is that I will not be doing the derivations that are involved right now. I will be posting these on your class page, but we will make use of some of the things that I'm going to be mentioning now in terms of the equations, and then we will look at a problem directly. Okay, all right. So I'm going to list or analyze the body's motion by just listing a set of rules or procedures for analysis. All right. So we look at procedures for analysis. And then we will appropriate this procedure for a very short problem. Okay, well, it may not be short necessarily, but we'll see. All right. Okay, so procedure for analysis is the first thing is that you draw the free body diagram. Of the rigid body. Okay, this is imperative. The second thing, and on the free body diagram, you mark all the external forces, you mark all the applied couple moments, you mark all the reaction forces. Okay, so you mark all the external loads and couples. Okay, and then you also mark the reaction forces and moments, or the reaction loads and moments. Okay, right? If a body is completely fixed, then it's going to have a reaction moment as well, right? So that's also something that you will have to mark on the free body diagram. So we will just call this as the FBD. So FBD involves all of these, and then you also dimension the problem. All right, so FBD involves all of these. Then the second thing is you also draw the kinetic diagram. This is something you've seen in particles, but there is a slight twist to it here. Okay, so draw the kinetic diagram of the rigid body. Okay, so the idea is here the focus is on the center of mass of the body. Focus on the center of mass of the body, or focus on the geometric center. So that's essentially what it is. Okay, and you mark two quantities on the kinetic diagram. Okay, so you mark the mass times the acceleration of the center of mass. Okay, this is called as the inertial force. Mass of the body times acceleration of the center of mass. Okay, so center of mass, I'm going to call it as G, or the geometric center, I'm going to call it as G. Okay, so here AG is the acceleration of the center of mass. Of the body, which precludes the fact that we need to know how to find the center of mass of bodies depending on how they are. Okay, if it's a rectangle or a circle, then it's easy to find it, but if it's a hoop or if it is in an odd shape, then we need to perform the integration and then find the center of mass. Okay, we will look at such options as well later. Then we also mark what is called as inertial torque. Okay, this inertial torque is given as Ig times alpha. Okay, and this is a torque acting on the entire body. Okay, so this is a torque acting on the entire body. I just want to specify a few things here. So Ig is the mass moment of inertia about an axis through the center of mass of the body. About an axis through the center of mass G of the body. Okay, and we will also have alpha, which is the acceleration of the rigid body, angular acceleration, of the body. Okay, the important thing is forces act at the center of mass. The inertial force is at the center of mass, drawn at the center of mass. So I just want to specify that here. So the inertial force, let me write this in this color here. So inertial force is at the center of mass, but the inertial torque is acting on the entire body because it's a torque, right? It's a couple moment. Couple moments act on the entire body. Okay, so the inertial torque, they act on the body. Okay, and in a sense, the inertial force is a resistance to translational motion. Inertial torque, you can think of it as a resistance to rotational motion. Okay, so inertial force you can think of as is the resistance of the body to translation. Okay, and then the inertial torque, my inertial spelling doesn't looks like a spooky inertial force, and then inertial torque is essentially resistance of the body to rotation. Okay, rotational motion. And the mass moment of inertia, this is also something that I'll describe a little more when we have our typical weekly meetings. But mass moment of inertia is a measure of the distribution of mass about the axis through the center of mass. Okay, so mass moment of inertia okay, this is a measure of distribution of mass about an axis. Okay, it's a very similar in idea and concept to the area moment of inertia, which you may have come across in strength of materials. Okay, there is not much to distinguish the two of them. They are derived in exactly the same way. You will use parallel axis theorem and so on if you need to in finding the mass moment of inertia about about a point about an axis passing through a different point. That is also completely the same as what you do for area moments of inertia. Okay, so in both these situations you're going to be drawing first of all the free body diagram, draw the kinetic diagram, and I'm going to call the kinetic diagram as KD, as you know. Okay, and here is a sample of the free body and the kinetic diagram. Okay, I just take an arbitrary body, some potato. Let's say that maybe I'm going to copy this and give it a slight thickness. Okay, let's see if that helps us. So here is the body, and let's see. Okay, and let me also draw the kinetic diagram of this body. Copy this and then paste it here. Exactly the same thing. Carbon copy. Okay, let me. Those hatches don't come out very well because it doesn't look like this is the body coming out of the page, but I hope it makes the difference. It's an arbitrary shape. Okay, does not matter what it is, of course. Then here is typically what I do. I have the center of mass of the body. Okay, center of mass of the body, which is marked here. So I'm going to take that and copy that and put that down there as well. Okay, so that's the center of mass, which we will call as the point G. Okay, so this is the point G. On the free body diagram, I'm going to have several forces acting on the body. Okay, so there is a force here, there's a force there, maybe there is a force there, maybe there is a torque that is acting on the body and applied a torque, or maybe I have a reaction torque, who knows, right? So I could have several forces acting on the body. Forces act at points, torques act on the body, okay? And let's say that this is M applied. Okay, so that's some kind of an applied torque on the body. Okay, and if needed, I can set up let's say a coordinate frame which is on the body here. Okay, so this is let's say the E1 direction, E2 direction. So let's see, this is E1 and E2. I'm just setting up some random coordinate frame. Okay, this is E1, this is E2, and then I'm going to have the third axis which is coming out of the page, which is E3, which is the same as the axis K, which is out of the page, so out of the page. Okay, and I'm going to grab all of these guys and put them on here as well. Okay, I needed to have, okay, that was weird. Okay, I need to capture this guy. All right, fantastic. Okay, beautiful, I got it. And here is the center of mass G, of course. Okay, so E3 is coming out of the page, so E1 and E2 are on the plane of the paper. So that's something that you want to note here. So the axes E1 and E2 are on the plane of the paper. Okay, and then two things that you're going to be marking on the kinetic diagram. So this is the free body diagram, as you can see. Okay, so this is the FBD. And then here is the kinetic diagram, which I'm going to draw in a second. Okay, so this is the kinetic diagram. On the kinetic diagram, that needs to be straight, I'm going to mark first of all mass times acceleration of the center of mass. Okay, so this is mass times acceleration of the center of mass. And then depending on what the angular velocity direction of the disk is, or if I don't know, I'm just going to assume a direction. I'm going to say that, okay, hey, there is a torque, okay, which is Ig times alpha, where alpha is a vector quantity, as you can see here. Okay, so Ig is the mass moment of inertia about the axis coming out of the page. Okay, so that's essentially what I have here. So this is the free body diagram, this is the kinetic diagram, and then I come up with the equations that help me look at how to analyze this body. Okay, I'm just going to grab that and bring it down here. So first equation, first set of equations is what are called as the translational equations, or force balance. In the force balance equation, here is what I say. Okay, the net force, or the resultant force on the body in its free body diagram, should be equal to the net force on the body in its kinetic diagram. This is called as force balance. This you know from particle kinematics. Okay, there is not much here. Then the kinetic diagram, if you look at it, what is the force? It's mass times acceleration due to gravity, right? That's the only force acting on the kinetic diagram. So I can actually simplify this and say, okay, hey, this is sum of all the forces on the free body diagram is equal to mass times acceleration of the center of mass. Okay, so this is one of the key equations. This is actually Newton's law, okay, as applied to the center of mass. So in this situation, you're treating the center of mass, or you're treating as if treating the body as if it is a giant particle whose mass is concentrated at the center of mass G. This is essentially the meaning of this force balance equation. But then, in particles, we were very happy with just this one. That's because particles don't perform any rigid rotations. But a rigid body has a certain geometric dimension to it, which means that it also has to perform certain rotations. So we have to include that. And this is the contribution by Leonhard Euler. This was by Newton, Isaac Newton. So this is Newton. And the modification of this equation to account for rotation, that is called as the moment balance. Okay, this is the same thing that you would have done in statics, as you recall. Okay, you did force balance, moment balance, except that in statics there was no motion, so net force was equal to 0, net moment on the free body diagram was equal to 0. Okay, here that is not the case. So this is to account for the rotation of the body. Okay, and here is what I can say. Sum of moments about any point on the free body diagram. So let me say sum of moments about the point G on the free body diagram. This has to be equal to sum of moments about the point G on the kinetic diagram. Okay, so where G could be any point. In this case, I'm assuming it to be the center of mass. Okay, so I'm just essentially saying that the net torque about any point on the free body diagram is equal to the net torque about any point on the kinetic diagram. Okay, and so this could be point G, or it could be a different point O, or whatever point you wish. Okay, so in this case I could choose different points if necessary. And since this is the case, if I choose the center of mass, right, look at this. On here, I know how to do the moments about a point on the free body diagram. I need to do the force times the distance, or if I have a couple moment, I just directly add it onto the mixture, right? But if I look at the kinetic diagram, if I have to find the moments about the point G, m times Ag is sitting at the point G, which means it's not contributing. So the only contribution is going to come from Ig times alpha, which is the couple moment. Okay, so this is, you can think of it as a couple moment, right? So this is going to be Ig times alpha. Okay, so this is another key equation. This is the contribution from Leonhard Euler. Okay, this was the contribution, of course, from Isaac Newton. So this is the contribution from Euler. Okay, then it also means that I can choose to some moments about a different point in the body. Let's see what happens here. Okay, let me take the same figure. Okay, this is the free body diagram. This is the kinetic diagram. I'm just going to copy this guy. Okay, I'm just going to bring this down here so that we can see what we're doing. Okay, let's say that I have a point somewhere here. Let's say a point C somewhere here. Okay, or a point O. Let's say this is a point O. I'm going to mark the same point on this body as well. So this is a point O. Okay, and let's say that I need to use the summation of moments equation about the point O. Then here is what I would say. Sum of moments about the point O on the free body diagram is equal to sum of moments about point O on the kinetic diagram. And let me assume that this distance is known to me. Okay, look at this. This distance is from point O to point G. So this is going to be R G slash O. Okay, so that I can write this equation now as the following. So this is going to be summation m naught on the free body diagram is equal to, look at this. I have a torque, an inertial torque, which is Ig alpha. So that's the first term that's going to come on here. So essentially think of the kinetic diagram as another free body diagram and see what are all the torques, what are all the moments about the point O. Now if I'm taking moment about the point O, then I know that moment is R cross F, right? Force cross product with the distance cross product with the force. So this is going to be R G slash O crossed with MAG. Okay, so this is going to be plus R G slash O crossed with MAG. Okay, so this is the second expression that I have. Okay, and so here is the basic idea. In summary, I have the following equations. Okay, so what are the equations that I have? I have the force balance equations. Okay, those are the same as before, what you did for a particle. That's essentially the same thing. Okay, so I'm just going to copy that and bring that down here. Okay, so this is one. And then I have the moment balance equations. So this is A, this is B, moment balance. I can do moment balance about the point G. If I do that, then I see that the net torque about the point G on the free body diagram is equal to Ig times alpha. Or if I do it at some other point, Okay, so this is at some arbitrary point, okay, which is O. Here this was at the center of mass, so let me cut that out. So this was at the center of mass, which is G. Okay, if I do it at some arbitrary point on the free body diagram, it makes no difference to me. This is like what you do in statics. I would just be choosing a different point to some moments. On the kinetic diagram, if you look at the kinetic diagram, you will have an inertial torque, the contribution from that, and as well the moment due to the inertial force. Okay, so that is RGO cross MA/G. Okay, so these are the things that you need. And so this is Euler's contribution essentially, and this is Newton's contribution. Okay, and this is Euler. And put together, these equations are called as the Newton-Euler equations. Okay, so put together, okay, they are called as the Newton-Euler equations. All right, and then once you're done with the force balance, you may also need information from rigid body kinematics and some force laws. Okay, so that's also something. I think this was supposed to be the second one, right? First one, second one. So let me say the third item eventually is that we will also need to perform rigid body kinematics and use information from force laws and so on. Okay, so this is something that we will need. And so I want to put this together on a very quick problem here. Okay, so let's say here is the problem. I need to obtain the equation of motion of a compound pendulum or a simple bar. Okay, so let me draw this here. So I have a fixed pivot point. Okay, let me call this point as the point O, and then on here I have a bar which is attached to the pivot, and it is swinging. Okay, let me make this as a thick bar, and here is the center of mass of the bar. It's right at its geometric center. I need to show it in a better way. So this is the point G, which is the center of mass of the bar. Okay, and let's say that the distance from point O to point G is a distance L. Okay, so at any point in time, let's say that this is a fixed distance of little l. Okay, so this is a uniform bar of mass m and length 2l. Okay, and for a uniform bar of mass m and length 2l, the mass moment of inertia will be given to us. Okay, so we are given, okay, Ig, the mass moment of inertia, as 1/12 ml square. Okay, so this is for a uniform bar okay, of mass m and length L. Okay, so which means that for us, let me maybe change the length to capital L so as to make a distinction here. So this is capital L. Let's say that the length here is not that. Let me do a few adjustments. I'm sorry. Length, let me bring it here. This is length 2 times capital L. Okay, so this is 2 times capital L. This is a generic formula. Okay, so this is a generic formula. Okay, or a generic expression. Okay, Ig is 1/12 ml square. So for our bar, Ig is going to be 1/12 times the mass times the length 2l whole square. Okay, because the length for our bar is 2l. Okay, which essentially tells me that Ig is, so this is going to be 4/12, which is 1/3. So 1/3 times m times l square. Okay, so this is Ig for our bar. So important thing is this is given for a uniform bar of mass m and length l. Okay, the length of our bar is capital L, which is 2L. Okay, so length of our bar is L is equal to 2 times L. Okay, so which is why we had that substitution done. So this is a common error, so which is why I want to point this out. All right, now this bar, as you know very well, it is rotating as a rigid body. It is going to have a single degree of freedom, which I'm going to call as theta. Okay, so the number of degrees of freedom, and we'll do a more elaborate analysis on the number of degrees of freedom and so on. For the time being, you know that this is a planar motion. If I locate the center of mass, that's good enough for me in terms of configuration coordinates, and then I can say that the number of degrees of freedom is only 1. Okay, so configuration coordinates needed is 2 coordinates are required. Okay, so 2 coordinates x and y required to locate center of mass G at all time. Okay, then the constraint is that the distance from point O to point G is a fixed distance. Distance from O to G is fixed, so it's almost like having a big pendulum sitting at the point G, as you can think of it. Okay, so which means that the number of degrees of freedom is 2 minus 1, which is 1, and so theta is our degree of freedom. Okay, so that's essentially what we have, and this is what we have done for particles also. What is my plan? Obtain the equation of motion. Okay, so that's essentially what I'm trying to do. All right, so I'm going to grab my figure here, and I'm going to come down here and then set up a coordinate frame and so on. Okay, so I'm going to have the IJK directions, as you know, your regular IJK directions. So this is J, then I'm going to have I, and then K, which is coming out of the page. Okay, so this is K out of the page. Position vector from O to G. Okay, I can write it in the following manner. Because I need the position vector, I need to perform some kinematics first. I can relate the acceleration of G to the acceleration of O. So that's why I'm doing the kinematics first. Okay, so here is point O, here is point G. Sitting at the point O, looking at the point G, I travel down and I travel to the right. Okay, this is L, this is theta. So this is L cos theta, L sin theta. And this is L cos theta. I'm not sure if you're seeing the gusts of wind or hearing the gusts of wind outside my window here. Pretty stark reminder that nature is so powerful. All right, so position vector from O to G is written as L sin theta I, L cos theta J. Okay, I'm going to assume that the angular velocity and angular acceleration of the bar is in the following direction. Okay, so this is alpha, this is omega, so I'm going to assume that omega is omega k, and then alpha is alpha k. Okay, we don't know, and we also know that because theta is the degree of freedom, this essentially tells me that omega is theta dot and alpha is theta double dot. Okay, so which can tell me further that omega is theta dot k, alpha is theta double dot k. This is the assumption that I have. Okay, I don't know what this is. My equation of motion is going to be in terms of theta. Okay, so the equation of motion should be in terms of the degree of freedom theta. Okay, it will of course have the weight of the body and so on, because I have a mass attached to it, right? I have a mass of the bar. So what do? I also notice already that the acceleration of point O is 0. It's a fixed point. Okay, and then point G and O are on the same body, which means that the relative velocity terms are 0. and relative acceleration terms are also 0. So I first relate the acceleration of g to the acceleration of O. Okay, so let me do that. I bring in my regular kinematics, acceleration of g, and this is typically how I start off all my problems. I always do the kinematics first. Okay, this is acceleration of O, alpha cross r g slash O, omega square r g slash O, and then all these relative terms will cancel off. Okay, so all those terms will be gone, this will be gone, acceleration of O is also gone. Just to do the substitution, acceleration of g is alpha theta double dot k crossed with L sine theta I, L cos theta j minus theta dot square times L sine theta I, L cos theta j. Bring in your triad I, j, k. So I, j, and k is my triad that I have set up here. Okay, so that I can write acceleration of g, collect all the I terms and the j terms. K cross I is j, k cross j is minus I, so I'm going to have L times theta double dot cos theta minus L times theta dot square sine theta in the I, and then I'm going to have k cross I is j, so that's going to be L theta double dot sine theta, minus and minus becomes a plus, L theta dot square cos theta in the j direction. Okay, so this is what I have for the acceleration. Alright, now I come to the position of drawing the free body and the kinetic diagrams. I'm done with the acceleration analysis or kinematic analysis. I don't have any force laws that I'm using here like springs or so on. I don't have any of them. There is no friction. Let us neglect friction. Okay, that's something that I will say here. Okay, neglect friction. I'm sorry I did not mention that, but we will neglect friction as well. Okay, no force laws as such. So I did the kinematics. Then I go to draw the free body and the kinetic diagram at some instant in time. Okay, so draw the free body and kinetic diagram, and kinetic diagram at some angle theta. Okay, where theta is a function of time, right? So at some angle theta as a function of time, and here is essentially what it is. I just bring my figure. I'm just going to copy that guy. Well, I can copy the entire thing. Let me copy the entire thing. Okay, and bring it down here. So this is the actual body. How does the free body diagram look? So copy that, draw that here. How does the kinetic diagram look? Copy that and draw that a little onto the other side. Okay, so these are the things that I'm going to have. All right, that's a pretty heavy gust of wind, I tell you. What are the forces? I have pinned reactions at the point O, right? So which means that I'm going to have some OX, and then I'm going to have OY. Okay, then what are the other forces? I'm going to have the force of gravity, right? So the force of gravity is going to be acting vertically down, so this is going to be m times g. Okay, and I also know the distances and so on, so I will be able to find what the angle theta is. I know the angle theta, right? So I can kind of write this down here. So this is the angle theta. Okay, so that I know the distance from here to there. This is the point G where the weight of the bar is acting. The weight of the bar always acts, has a line of action passing through the center of mass. Okay, so this distance is capital L. So this is going to be L times sine theta. Okay, as you know. All right, so these are the forces on the free body diagram. That's about it for the free body diagram. There is nothing else going on. How is the bar set in motion? It is set in motion by means of certain initial conditions, which I'm not worried about at this point in time. Kinetic diagram, two things. Okay, I first of all bring in my acceleration expression. You see, acceleration has a component in the I direction and the j direction. So let me do something here. Before I go ahead and mark the kinetic diagram, I'm going to take this guy and I'm going to bring that down here, cut this off, and I'm going to say, okay, hey, this one I'm going to call as AGX, and this term I'm going to call as AGY. Okay, so if I draw mass times acceleration, m times AG will then becomes m times AGX in the I, m times AGY in the j direction. So when I'm marking the forces on the kinetic diagram, I'm going to draw two forces at the center of mass, of course, at the center of mass g. I'm going to have a force m times agx, and then I'm going to have a force m times agy. Now who says this is pointing up? I don't know. Okay, this is m times agy. Okay, this is all happening at the center of mass g. What else do I have? I have the inertial torque, which is ig times alpha. Okay, so that's also something that I have. And since I have assumed alpha to be counterclockwise, this is going to be ig times theta double dot. Okay, so this is the kinetic diagram. So free body diagram, what are the forces? The weight of the bar, which is acting at the center of mass. Then the pin reactions, which are at the point O. Kinetic diagram, I have the inertial force, m times ag as a vector, but the vector is split into components in the x and the y direction, and then I have the inertial torque, which is acting here, ig times theta double dot. What do I do next? Then I think, equation of motion should not contain the constraints. These are constraint forces, right? The reaction forces. These are constraint forces. Let me write them down. So these are constraint forces. Okay, equation of motion should not contain the constraint forces. So if I start summing forces up, that is not very useful for me, which means my only point of view is to start summing moments about the point O. Okay, I'm going to write this down. Okay, so the equation of motion should not contain constraint or reaction forces. Okay, so which means that if we used summation of forces on the free body diagram is equal to m times ag, then this would include the pin supports at O. Okay, so this is not useful for us. Alright, so which means that in order to make the problem more useful for me, I'm going to sum moments about the point O. Okay, so which means that to get rid of the pin reactions in the equation of motion, I'm going to sum moments about the point O on both the free body and the kinetic diagram. I'm going to bring in the rotational equation, okay, rotational or moment balance equations. Okay, so this implies that I'm going to do moment balance about the point O. Okay, that's about all I'm going to do. So I'm going to bring my free body and kinetic diagrams once again down here. Okay, so I'm going to copy that and bring it down here, and then we will start on our merry way to summing moments about the point O. Okay, so here is the free body diagram, and then here is the kinetic diagram. Okay, so then I say, hey, sum of moments about the point O on the free body diagram is equal to sum of moments about the point O on the kinetic diagram. Alright, so where is the point O on the kinetic diagram? This is the point O. Now, do I know these distances to these forces? Of course I do, right? Because I know the angle is theta. So I can write these distances in the following manner. So watch this. This force times that distance here. That's going to be the length L. This angle was theta, right? So that's going to be L times sine theta. And for this force MAGX, the length all the way from here to there. Let me make sure that's aligned this way. Okay, so that's the perpendicular distance, right? As you can see, that's going to be L times cosine theta. Okay, because this angle here is anyway theta, and this length was capital L. So since I'm doing it in a planar manner, I'm going to do it using clockwise or counterclockwise rotations. So I'm going to say counterclockwise rotations are positive, counterclockwise rotations are positive. Okay, when I'm doing the summation of moments. Look at this. M times G about the point O, if you use a right hand rule, that's going to be a clockwise rotation. So in the free body diagram, I'm going to have minus mg times L sine theta. That's about it. Okay, on the kinetic diagram, I'm going to first of all have the inertial torque. So that's the first thing I'm going to be putting, Ig theta double dot. That's like a couple moment. Okay, so think of this as a couple moment. Okay, think of this as a couple moment. And then I'm going to have contributions from MAGY and MAGX. Look at that. They are going to produce both of them counterclockwise rotations. So this is M times AGY times the distance of L sine theta. And I'm going to have M times AGX times L cosine theta. Okay, so this is the moment balance that I have essentially when I'm doing the moments about the point O. Okay, these are all on the free body diagram. These are all coming from the kinetic diagram. Okay, so these are coming from the free body diagram. And I already know AGY and AGX, right? So I'm going to start substituting. So first of all, IG, I had found it to be 1/3 M times L square. Okay, so this was calculated earlier on. And then I'm going to have AGX, AGY, okay, which we had written down here. Okay, so I grabbed them from here. So I'm going to bring these creatures, copy that. That's going to be AGX, okay, and then AGY. You'll see that this is just a lot of algebra. That's about it. After some time, there is not much to it once you have written the moment balance. Okay, this is AGY. Then start doing the substitutions. So minus M G L sine theta is equal to 1/3 ml square theta double dot, and then M times L sine theta times AGY, which is L theta double dot sine theta L theta dot square cos theta. And then I'm going to have M times L cos theta times L theta double dot cos theta, which is AGX, minus L theta dot square sine theta. Okay, then do the simplification. The mass cancels off everywhere. That's gone, that's gone, that's gone. Okay, one of the lengths can cancel off, so I can cancel off this guy, take the factor of 2 there. The length is gone, the length is gone. Okay, so what do I have now? I'm going to have the following. Okay, so this is minus G sine theta. This is equal to 1/3 ml theta double dot, and then M is gone, I'm sorry. I forgot about that. Okay, this is 1/3 L theta double dot plus, look at this. This is sine theta. A factor of L is a common factor, so I'm just going to take a factor of L outside. This is sine theta, theta double dot sine theta, so theta double dot sine square theta. And then I'm going to have theta dot square sine theta cos theta, and then plus L times cos theta, theta double dot cos theta, so theta double dot cos square theta, minus theta dot square sine theta cos theta. And you can obviously see that this term and that term will cancel each other off, and so I'm left with the following very nice thing. Minus G sine theta is 1/3 L theta double dot plus L theta double dot times sine square theta cos square theta, which is equal to 1. Okay, so 1 plus 1/3 is 4/3, and so I get the following. Minus G sine theta is 1/3 L theta double dot plus L theta double dot, because this is equal to 1. Okay, so this is 4/3, and I can rearrange some of these things. So I get theta double dot is equal to minus 3G by 4L sine theta. Okay, and this is the equation of motion, and this is very suspiciously similar to the equation of motion of a simple pendulum, okay, which when you had a particle. Okay, so this is the equation of motion. All right, and so just to recap whatever we have done so far. Okay, very quick recap of what we've done so far. I'm just going to go from the first page here. So in rigid body kinetics, we're going to be looking at the relationship between forces and the motion of the rigid body. Okay, we're going to have a procedure for analysis where we draw the free body diagram and the kinetic diagram. On the free body diagram, we mark all the forces and all the couple moments that you apply. And on the kinetic diagram, I'm going to have mass times acceleration at the center of mass, which is the inertial torque, inertial force. Okay, so this is the inertial force. Okay, and then this term is the inertial torque. Okay, and this is how you perform the analysis by first of all saying, okay, I can do a force balance, which is sum of all the forces in a free body diagram is equal to that in the kinetic diagram. You did this for particles earlier, and now you're going to do it for rigid bodies, so you got to do an extra equation, which is the sum of moments about any arbitrary point. Okay, so net torque about any point on the free body diagram. Okay, this is equal to net torque about any point on the kinetic diagram. Okay, and this is the consequence of Leonard-Euler's contribution. And so in summary, you have two equations: translational equation, rotational equation. The rotational equation can be done at the center of mass or at any other point in the body. And then we also need to perform rigid body kinematics, which is why we did kinematics in the first place. Okay, and then some force laws if you have friction, or if you have springs, if you have rolling without slip, and so on. Okay, so we need to have those kinds of force laws as well coming into play, which we will do in future problems. A very quick problem here: a compound pendulum or a simple bar of mass m and length 2l, which is sitting and oscillating about a fixed pivot. How to come up with the equation of motion? Mass moment of inertia is given. This is a generic formula for a uniform bar of mass m and length l. We adjusted that for our bar because our length was twice the given length of the formula. Okay, so our equation looks slightly different there. And then I say, okay, how many configuration coordinates? 2, to locate the center of mass. If I know where the center of mass is, I know where the body is. But then there is a constraint: the distance from point O to point G is a fixed distance, so that the number of degrees of freedom is 1, and theta is our degree of freedom. And then I perform some kinematics because I know the acceleration of O is 0. I try to relate the acceleration of G to the acceleration of O. This is something I do for every problem that I solve. And I assume angular velocity, angular acceleration directions related to the degree of freedom. Then go ahead and I write down my free body and kinetic diagrams. Mark the inertial forces, mark the inertial torque, mark all the applied forces, mark all the reaction forces. I don't need reaction forces included in my equation of motion, so I don't want to do the summation of forces, because if I sum forces, I get the reaction forces in my equation. So how to get rid of it? I sum moments. So I look at moment balance. I choose all counterclockwise rotations to be positive. I already know m-agx and m-agy in terms of the degree of freedom theta. I apply that. I do summation of moments on the free body diagram about the point O. Set that equal to point O on the kinetic diagram. Move on with your life. Calculate this. Cancel off some of these common terms which are positive and negative. Apply the identity, and here you go. This is the equation of motion, and this is very elegant. In many ways, it is very similar to the equation of motion of a simple pendulum. Alright, so in future videos, we're going to crank up the level of the problems, and then we're going to look at more and more nicer problems, as you will see. I hope all of you are staying safe. Take care of yourselves. Have a great day. Bye-bye.